Welcome back. This is The Lord's Maid. Let us rejoice, be glad in it. In this video, I'm going to talk about work done by electric fields and also about electric fields in general, plus Coulomb's law. All right, so first, electric fields, going back to what we just talked about in the previous video, atoms can gain or lose electrons, and then we could have a substance that has a net gain or net loss of electrons, and they have this charge. If you're a charged object, then you produce this electric field around you. All right, so if you're a charged atom or a charged surface or a charged object, you produce an electric field. It's like gravity, but in the case of gravity, the field it generates, it's based off how heavy the object is. So if you're a more heavy object, you have a bigger gravitational field. In this world here with electricity, it's all about how big your charge is and how tiny you are. So if you have a big charge, lots of extra electrons or a deficiency in electrons, you can have a very, very large field around you. So you can also think about electric fields being very strongly related to voltage. They're not exactly the same thing, but they're close enough for your knowledge that you work with this idea that an electric field is kind of like, well, what's the voltage? And like a high voltage would be like a high electric field. So now the first person to talk about electric fields, or I don't know if he was the first person, but one person who's given a lot of credit for working with this is Benjamin Franklin. Because Benjamin Franklin had to make a choice whether he thought it was a positive or the negative that moved, he chose that the positive moved. Ever since then, we've had electric fields point towards the negative. So if you're looking at this little diagram here, you'll see that this positive particle has an electric field that emanates around from it, and this negative one has arrows pointing towards it. So the electric field leaves the positive and comes to the negative. All right, that's because Benjamin Franklin said that the positive charge are moving. And because we didn't change a thing, we've been using that ever since. So this, if you have two particles next to each other, if you have just an individual positive proton here, you can see that the positive, it's kind of hard to see. Sorry, zoom in a little bit right there for you. If you just have a positive particle, everything just leaves. And if you have a negative particle, everything's coming in. Again, big idea is the higher the charge, the larger the field around it. So if you have again, let's go back to chemistry a little bit here. Think about like solubility. Why are some things soluble, some things not soluble? It comes down to what's your voltage around you? What is your electric field strength? How sticky are you? You might remember from chemistry that the bigger your charge, the less soluble you are. So like things with the +2 and -2 charges coming together tend not to dissolve, but things with the +1 and -1 charge are always soluble. So again, think about the rules on the solubility chart. All alkali metals are soluble. Why? Because they only have a +1 charge. In general, most -2 charge things, most sulfides are not soluble. Why? Because there's a bigger voltage, and so they're more sticky, and so they can't dissolve in as well. So this also goes back to like strong acids and why hydrofluoric isn't one. Fluorine is super electronegative. He's really negative and he's really tiny, which results in that hydrogen just left him. You want to come back. And that's the real life connections there. Fluorine, he should be a strong acid because he's really electronegative and very polar with this hydrogen, but the hydrogen can't help himself but come back to the really negatively charged fluorine, which has the high voltage around him. So, but again, electric fields are just the idea that if you're a positive or negative charge, you have some field around you that can push or pull things away from you that are also charged. When we talk about how strong it is, electric field strength is measured in newtons per coulomb, which is to say, what force would this particle feel inside this field based off its charge? All right. So you can rearrange this, think of it like this. Here, the force will be in newtons. The Q here is the charge. E is electric field. This is basically saying that, okay, what force will a particle feel if it has a certain charge and electric field is a certain strength? All right. So electric field strengths are measured in newtons per coulomb. So how much force would be required to move a charged particle in the field? Well, it kind of depends, kind of back to gravity. If you want to move something, and with gravity, it comes down to how heavy they are. If you want to lift a block that's heavier, it takes more force. In the electric world, how big is that charge? The bigger the charge you want to move, the more force it's going to take. It also depends on the electric field strength. If the electric field is stronger, then it's harder to move it too. You can think of that like Jupiter's gravity versus Earth's gravity. It's harder to lift a block on Jupiter because its electric field strength is larger. When you think about the field generated by an individual substance, like just a charged atom, the field strength is no different than the gravity equation. We'll get to that later, but for now, you just think of it as the field strength equals K, which is a constant. Q is going to be the charge of the atom, and D is how far away the substance is. That'd be like where your field strength is located at. So we'll discuss that more later, but for now, if you want to know the field strength for an individual atom, you got this K constant, which is really large. Again, comparing that to gravity, gravity's constant is 6.67 to the negative 11th. This constant here is 9 billion. So it's about 20 orders of magnitude larger. It's very, very much stronger. This explains why a comb can pick up pieces of paper off of Earth, because you put the comb through your hair, picks up a charge, put the paper above some little piece of paper, and the stack electricity will bring them right up. It's big Earth versus small comb, and the comb wins because this difference here. Anyway, so K constant times what is the charge of the substance in coulombs and how far away is it? This will tell you what the field strength is for an individual atom. Now, going back to the gravity, the work done depends upon, in gravity, it's how heavy is it, how high you're lifting it. It's kind of like that here too, but instead of like lifting things away from Earth, we're lifting away from a charge. And instead of like worrying about the mass of the particle, we worry about the charge of the particle, because the more charged it is, the harder it is to move it. And so our equation for figuring out how much work it takes to move a charge is the work equals what is the charge of the particle you're moving and what voltage change are you going over. The voltage change would be the difference in electric field strength. As you move from one place to another place, how much has electric field strength changed by? Let's go back up to electric fields again real quick here. So, I'll come back to that later. So think about this here. We have a positive plate and a negative plate, okay? And we can talk about the work done. Think of this like gravity. So we have some positive charges, a positive Q. We have two that are the same, and this one's supposed to be bigger, okay? These positive charges want to fall down towards the negative. Well, how much energy would be released by this? Well, if you compare these two here, this one here is closer to the ground, which means when it falls, it doesn't release so much energy. This one here is higher, so as it falls down, it's going to go through a larger change, and it's going to have more energy released. The bigger charge would also have more energy being released as well, because it's just heavier. It's not really heavier, it just has more charge. So the work done would be larger there. So here we can think of it again too. If we have voltages, different voltages at different places here, moving things around kind of comes down to what's the change in voltage. Again, think of this as being the height. It's flipped on its side, but think of like, if these were all like positive particles, they would want to go towards the left, and that would be releasing energy. And the amount of energy that would be released depends upon how high they're falling from, which again would be the voltage. So if E fell all the way down to the 0 volts, that'd be 50 volts. If D fell down, it'd be 40 volts times whatever's charges, that'd be the work. Same story going back the other way, it takes energy to lift it towards the positive plate if it's positively charged. So the work that's being done on a charged particle depends on how charged it is, which again would be like its mass and gravity, and how much voltage, which would be how high you're going to lift it. So Coulomb's law, this is a really important equation. This is basically the force of attraction or force of repulsion between two charged particles. The force that two particles would feel against each other comes down to this K constant, again, which you mentioned briefly earlier, which is this big number, both of the charged particles and how far apart they are. So this also notes then, if you are not charged, if you're neutral, you're pretty much immune to this. You're not going to be feeling those forces. Now, we should mention that things can be polarized, and we can cause the positive negatives to split a little bit, which can result in a little charge separation, resulting in a smaller force. But for the most part, if you're neutral, you're pretty much safe. Again, this equation looks a lot like gravity's that we had learned about first semester. The only thing different is instead of a capital G, we got a K. Instead of having masses on the top, we have Q's. That's the only difference. Again, just like gravity, if you want to know the gravity equation, in first semester was lowercase g, which was the field strength, equals capital G times the mass of whatever it was, divided by the distance. So, in this video again, what I wanted to do is I wanted to talk about electric fields. Again, big things to take away from this. Electric fields, they point towards negative. The more condensed the charge, the larger the charge, the bigger the voltage, the bigger the field strength right there. The amount of force it takes to move a particle inside of a field depends on what's the size of the charge and what the electric field strength is in that location. And when you're moving things, when you're actually comparing it to work is equal to how big is that charge and how far are you moving in terms of voltage differences. Which also we should mention too then, if you're not changing voltage, if you're just moving a particle along the same voltage line, it takes no work. This also explains why electrons can orbit the nucleus without ever actually losing energy. As long as they stay on the same electric field strength line, it takes no work to move them. It's like a frictionless surface. All right. God's peace. Have a great rest of the day.